Yeah, good day to you all. In this session today, we will continue on what we had seen in the previous lecture on the topic of non-isolated converters. In the previous lecture, we had gone through some of the rules that govern the connection of storage devices with switches, and we came across a very simple basic converter cell, which is what is shown here. This basic converter cell consists of one single pole double throw switch and one inductor, and we called this as the basic power converter cell. And we had seen in the earlier lecture how this power converter cell is connected with a source and a load, a source consisting of a DC voltage and a load consisting of a resistive load, which is supported by a capacitor to filter out the switching frequency, ripple current and ripple voltage. The single cell which we had seen in the previous slide, which we called a basic converter cell, can be connected with a source and a load as a buck converter. We had seen in the previous lecture that this converter has a voltage conversion ratio V0 by Vg, V0 by Vg equal to D, duty ratio, and this duty ratio is always less than 1. And on account of this relationship, this type of converter is defined as the buck converter or step down converter. You can get an output voltage which is less than the input voltage, and that is the reason why this is called a buck converter. The switching cell that we had defined is what is in the middle, which consists of the switch plus the inductor, and it is possible to convert this converter, this buck converter, which has a V0 by Vg of D, into a different type of power converter. So, before that, we will look at all the other relationships that we had seen in the step down converter or buck converter. It has a voltage conversion ratio V0 by Vg indicated by D, and it has a current conversion ratio, that is the ratio of the output current I0 divided by the input current Ig as 1 over D. And we also saw that the product of these two numbers, V0 by Vg and I0 by Ig, is the efficiency of the power converter, V0 I0 by Vg Ig, and because these ratios are inverse of each other, the power conversion efficiency in the buck converter or the ideal power converter is unity. This also we had seen, and the ideal purpose of a power converter is to convert a voltage Vg to another voltage V0, and in this converter V0 is less than Vg, and it draws power from the source and delivers it to the load. But this kind of converters also have several non-ideal performance features. One of them is that the current that is supplied to the load is not perfectly constant DC. It has a ripple which is given here as delta I0 by I0, the ripple factor, and this factor we had seen that is a function of the operating duty ratio D, 1 minus D, and it is a function of the switching period Ts, and it is also a function of the time constant of the converter L by R. And this non-ideal current ripple will be quite small if the ratio of switching period to the L by R is much less than 1. This non-ideality can be neglected. Another non-ideality in the converter is the voltage ripple at the output. Ideally, we would like this power converter to provide an output voltage which is constant, fixed, and with no other disturbances. But because the power is processed with a switch here, the converter provides an output voltage V0 which also has undesirable ripple delta V naught, and this ratio delta V naught by V naught is a non-ideal property of the converter. And we would like this delta V naught by V naught to be as small as possible, and that is possible if we make the switching period of the converter Ts very much less than the natural time constant of the converter, which is root of L by C. If Ts square divided by LC is a small small fraction, then the voltage ripple also will be a small quantity. And we saw that in these converters, the output voltage under ideal circumstances is D, but there are several non-idealities in that converter, namely the switch voltage drop Vt, the diode voltage drop Vd, and then the source resistance Rs, and then the resistance of the inductor RL, and the non-idealities associated with every one of these elements, the switches, the source and the inductor, results in the output voltage being different from the ideal value of D. And we saw that this correction factor on account of the non-idealities can be represented as a multiplying correction factor, which consists of, in the numerator, an expression which is dependent on the switch drops and the duty ratio, and in the denominator it depends on certain ratios of resistors and the duty ratio. And in a good converter, this correction factor must be as close to 1 as possible. And we also saw that on account of this voltage not being ideal, the devices not being ideal, the power is not processed with zero losses. The output power by input power, which is defined by the efficiency of the converter, now has a number which is less than 1. To that extent, we lose some power in the converter, and in a sense, these were the steady state performance characteristics of the buck converter. We had spent quite some time in going through these processes and finding out in operation what are the non-idealities, how they are accounted for, and finally how they are related through the voltage gain, through the duty ratio for voltage gain, current ripple, voltage conversion factor, then efficiency and so on. In this lecture, we would continue with some of the same methods, so that many of the analysis methods that we had learnt in the first lecture, we will reinforce further by looking at the new type of converter. Again, this slide also is about the voltage conversion ratio of the step down converter. What you see in the red line is the ideal voltage conversion ratio. It is a function D. So, the voltage conversion ratio on the vertical axis is plotted as a function of the operating duty ratio. The red line is D, which is a 45-degree line. When duty ratio varies from 0 to 1, conversion ratio also varies from 0 to 1. And we saw that because of several non-idealities, there is a drop in the conversion factor, and this also is the same as the efficiency of the power converter. So, in the non-isolated buck converter, we had seen many of these things. Now, we will try to see the other converter topologies which are derived from the same switch cell. The cell that we had used in the first lecture was the buck converter, where the cell was used with the switch on the source side and the inductor on the load side. In two other ways the cell can be used, where the inductor can be on the source side and the switch can be on the load side. And we could also have a third method of connecting the switching cell to the source and the load, where one of the poles is connected to the source, the other pole is connected to the load. So, there are several variations of this switch cell. The one with the poles on the left hand side, the throws on the left hand side and the inductor on the load side, the inductor on the source side and the throws of the switch on the load side, and then the third one that I had shown here. These are the three variants, and the buck converter, the step down converter, we might define as a voltage input and current output converter, because on the input side the voltage is constant, on the input side voltage Vg is defined, and on the output side the current I naught is defined. So, this could be also defined as a voltage input current output converter. The second converter that we would like to see today is the current input voltage output variant, where the input side current is stiff. From the source we draw a nearly constant current because of the presence of the inductor on the input side, and then on the output side this current is being used to charge a capacitor, so that the output side has the voltage to be stiff. So, we might define this converter as current input and voltage output variant. The third variant is shown here, where the input side current is also stiff. When the switch is connected to the source, nearly constant current is drawn because of the inductor's presence, and when the switch is connected to the load side, nearly constant current is supplied to the load side. So, you can say that the switch, while it is connected here, draws energy from the source and then dumps it into the load, and on both sides the current is defined, and so this can be called a current input current output variant. The three variants have these names as step down or the buck converter, which is this converter, then the boost converter, which is the second variant which we will see in detail today, and the third one is the buck boost converter or the current input current output converter. So, in today's lecture we will spend a lot of time trying to find out the various steady state performance functions of the boost converter. Okay. This converter has the name boost converter, and we will spend some time to find out why it is called a boost converter. We will also go through the entire process of steady state performance analysis of the converter. We will follow the very similar pattern that we had done for the step down converter, going through V naught by Vg, I naught by Ig, and so on. The idea is to make sure that we fully internalize, we fully absorb the analysis methods for the steady state performance of any converter. The steps that we had gone through earlier are the same as the steps that we will go through now. We would like to see what is the voltage gain, V naught by Vg, that is the output voltage expressed as a ratio of the input voltage Vg, and similarly the current gain. In what way the output current I naught, the load current I naught is related to the source current Ig through the switching duty ratio D, and the ideal performance of the converter is to draw steady power from the source and deliver steady power to the load. But because we are using switches in the converter, power is being drawn intermittently and it is delivered to the load intermittently, and the purpose of the inductance and the capacitor is to smoothen the power flow. So, on account of that, we will get what we want, namely steady state average output voltage and steady state average output current, but on all these quantities, on the output voltage V naught as well as the current I naught, we will have a switching ripple. The inductor current, which is supposed to be steady and constant, will have a ripple which is delta inductor current or the ripple current in the inductor. Similarly, the output voltage, which is supposed to be steady and constant, will have a switching ripple present on that. So, we would like to see again each one of these performance factors. These two are the desirable quantities and these two are the undesirable quantities, but we would like to know how much they are. And in the next step, we would like to see what are all the non-idealities present in the converter. The switch has certain non-idealities. During conduction, the voltage drop is not 0. The source has impedance. The storage components like inductors and capacitors have resistors parasitic resistors, what is the consequence of all these non-idealities, and then finally how does it affect the power conversion through the efficiency. This is something which we had done before in the case of buck converter. We will do it again so that we fully internalize the method of steady state analysis. The first concern is the voltage conversion ratio, which is V naught by Vg. The converter is now operated in pulse width modulation technique, where Ts is our total switching period. In that we have a duration called T on and we have a duration called T off. So, during T on, the switch is connected between P and T1, and during T off, the switch is connected between P and T2. So, if you see the switch cell here, during on time, the switch is connected between P and T1, and during off time, the switch is connected between P and T2. And one switching period is Ts, 0 to Ts is one switching period, and within each switching period there is a duration called on time and a duration called off time. On time, during on time energy is drawn from the source, and during off time the energy is passed on to the load. And how this operation takes place, we had already seen in the case of buck converter. We will see again in this converter, and we would like to find out ideally what is the voltage conversion ratio, what is the current conversion ratio, and so on. We had seen that the voltage conversion ratio of any power converter is always obtained by applying the principle of volt second balance on the inductor. This is the first step in finding out the ideal voltage conversion ratio. So, in order to do that, we draw the voltage across the inductor for one cycle. Under steady state, we draw what is the voltage that is applied across the inductor in the converter for one cycle. We can see that during the on time Pt1, when the switch is on, the voltage across the inductor is Vg, what is shown here. And during the off time, when the switch T2 is connected, the voltage across the inductor is negative, and it is this Vg minus V naught. The volt second balance is in a sense indicating that the voltage across the inductor on an average has to be 0. In every cycle, the inductor's net voltage and time applied is 0. So, this can be seen here as the hatched region. Whatever is the voltage time product applied to the inductor during one part of the cycle in one polarity is the same as the volt second which is applied across the inductor during the other part of the cycle. So, that over one cycle, this positive area what you see here and the negative area that you see here are same. The positive area is Vg multiplied by T on, and the negative area is Vg minus V naught multiplied by Ts minus T naught, and that is what in a sense means inductor volt second balance. And this can be mathematically written as the volt second during on period and the volt second during off period adds up to 0. In one cycle, the net volt second has to be 0, or the positive volt second and the positive volt second and the negative volt second have to balance each other. So, this if we expand, we will see that the ratio V naught by Vg is the same as the ratio of Ts by Tf, that is switching period divided by off period, which can be expressed as 1 by 1 minus d, where d is the duty ratio of the switch, and this duty ratio is T on divided by Ts. In the first converter that we had seen, step down converter, this ratio was D. Duty ratio directly determined the ratio of output voltage to input voltage. In the boost converter, this ratio is 1 by 1 minus D. We can see it in the form of a graph, this relationship of V naught by Vg here on the y axis as a function of D on the x axis. D varies from 0 to 1, and when D varies from 0 to 1, V naught by Vg in the ideal case varies from 1 by or varies as 1 by 1 minus D, or when D is equal to 0, the gain is 1, and when D is equal to 1, the gain is infinity, very large. When D is equal to exactly 0.5, you will find that the gain will be 2. 1 by 1 minus 0.5 is 2. So, when duty ratio is 0.5, the gain is 2. When the duty ratio is 2 by 3, gain will be 3, and so on. So, this is the relationship which determines what will be the voltage conversion ratio of the converter. We see that it is all the time, right from 0 to 1, for all duty ratios, the output voltage is more than the input voltage. V naught by Vg is greater than 1, or V naught is always greater than Vg in the entire range of the duty ratio 0 to 1, and that is the reason why this converter is called a boost converter. It boosts the input voltage to a value which is higher than the input voltage, and that is the reason for the name boost. It is also called step up converter or a boost converter. Okay. The second relationship that we would like to see is the ratio of Ig to I naught, and this is obtained, as we had seen before, by finding out the current conversion ratio. How much of this current is transferred to the output side and how much of that is being delivered to the load. So, if you see this picture, here you can see that the inductor current, if it is considered constant, during the off time it is delivered to the output circuit. During the on time, the inductor is freewheeling on the source side. So, I naught t can be plotted as a function of time. During the on time, no current is being delivered to the load, 0 current, right from here to here, and during the off time, t on to ts, the full current of Ig is delivered to the load. So, naturally, this I naught of t, when you average it, it will be the same as the output current, because the average current through a capacitor is 0 over 1 cycle. So, if we apply that principle, you will find that Ig into T off is the average of this quantity, which is same as I naught into Ts, and this is obtained by finding out the average output current being delivered by the converter, and this relationship can be reduced to get Ig by I naught is 1 by 1 minus D. This is again something which we had seen before. The forward voltage converter conversion ratio V naught by Vg will be the same as the reverse current conversion ratio Ig by I naught. This is because V naught I naught is equal to Vg Ig in an ideal converter. All the input power is the same as the output power, and because of that we will find that the ratio of V naught by Vg is the same as the ratio of Ig by I naught, which is what we have seen here as 1 by 1 minus D. The efficiency, ideal efficiency of this converter, as before, can be seen. It is a product of V naught by Vg into I naught by Ig, and these two functions are inverse of each other, and you get the ideal efficiency to be unity, because there are no energy dissipating elements inside the converter. There are several non-idealities in the converter. The non-ideality, two non-idealities which we wanted to understand in the sequence in which we are going are, first, the non-ideality in the inductor current, delta IL by IL, or in this particular case it is delta Ig by Ig. The inductor current ideally should be constant and steady, but because of the switching it will have a ripple, and we define that ripple current as delta IL, and the ratio of delta IL by IL is a measure of this non-ideality, and this can be evaluated simply by integrating the inductor voltage, because L di by dt is V is the relationship for any inductor, and if we know the voltage across the inductor VL, integral of that will provide us the current through that. So, what I have drawn here is the voltage across the inductor. When the switch is on, voltage across the inductor is same as Vg during the on time, and when the switch is connected to the off pole, the voltage across the inductor is negative, and it is Vg minus V naught with a negative sign, and integrating this will give us the required inductor current, and what you see is the integral of the inductor voltage waveform. As expected, a steady voltage when integrated will result in a ramp. So, this would have a slope of Vg by L. L di by dt is Vg in the first half, and in this region the slope will be di by dt is V naught minus Vg divided by L, and it is a negative slope. Okay. This is the magnitude of di by dt. And for steady state, the ripple in the positive rising half is the same as the ripple in the falling half. So, we might find out this delta IL is nothing but Vg by L, which is the slope, multiplied by the on duration, which is dTs. So, this inductor voltage, inductor current ripple in all the inverters is found out by drawing the inductor voltage and integrating the same. And in all cases, because the voltages are nearly constant, this integration will result in a simple ramp, and algebraically it is possible to find out what is delta IL. This delta IL is, if you replace Vg as V naught into 1 minus d, this quantity in terms of V naught is V naught into 1 minus d divided by L into dTs, and the inductor current itself, we have seen the ratio that IL is I naught by 1 minus d, I naught is V naught by load resistance. So, if you combine all these things together, the current ripple factor, which is ratio of the ripple current divided by the inductor current, is now 1 minus d square multiplied by a ratio which is Ts by L by R. Ts is the switching period, L by R is the time constant of the load and the inductor. Now, if this ratio Ts by Lr is very small, or if we switch at a high enough frequency, it is possible to make this current ripple as small as possible. So, this non-ideality of inductor current ripple can be reduced arbitrarily to any small level by selecting a switching period which is very small, or selecting a switching frequency which is very high. Okay. The condition for this low ripple current, as I had said before, is that the switching period has to be very small compared to the time constant of the inductor and the load L by R. This will ensure that our converter is working close to ideal conditions. The switches in the converter are not really ideal, and they are realized by a active switch transistor on this side and a passive switch which is diode on that side. And these switches have a voltage drop during conduction, which is Vt for the transistor and Vd for the diode. Now, on account of that, our V naught by Vg is not going to be the same as what we had found out ideally. Ideally, V naught by Vg has to be 1 by 1 minus d, but because of the non-ideality in the switch, V naught by Vg will be not equal to 1 by 1 minus d, and we would like to find out what is this effect, to what extent we will not get the ideal performance, and by how much we will be away from the ideal performance. We now take into account the switch drops while calculating the volt second balance. The method is the same, but we have to make sure that we correctly account for the voltages across the inductor. When the switch was ideal, this was only Vg, but now it is Vg minus Vt. When the switch was ideal, during the off time, the voltage was just simply Vg minus V naught, but now you have another term which is the diode drop. So, if these are all taken into account, the method of calculation is as simple as before. The area of the volt second given to the inductor during the on time is the same as the area of the volt second taken from the inductor during the off period, and this gives the relation Vg minus Vt into on time plus Vg minus Vd minus V naught into off time, and this total adds up to 0. And this is now the fresh volt second balance taking into account the non-idealities of the switch, and when that is done, this expression results in V naught by Vg is same as the ideal multiplied by a correction factor. And you can see that this correction factor is less than 1, because from 1 you have to subtract two positive ratios, Vt by Vg into d, Vd by Vg into 1 minus d. So, this ratio will be small if the switch drop is very much less compared to Vg, this ratio will be very small if Vd is very much less compared to V naught. This Vg by 1 minus d is V naught. So, we can say that Vt has to be very much less than Vg, Vd has to be very much less than V naught. So, if this inequalities are true, then the correction factor will be close to unity, and this correction factor is also the efficiency of the converter, and efficiency also will be close to unity, and we will have a small factor by which it is different from 1, and that will contribute to the total losses. So, the method of calculating the voltage ratio has not changed, but the accounting is now more proper. The switch drops also are taken into account. The current ratio does not change because of the switch drops. This also is a property which we have seen. Any non-ideality which is coming in series in the converter will not affect current ratios, and so the ratio Ig by I naught remains as before 1 by 1 minus d, and as a result the correction factor on voltage is also the same as the efficiency. So, what we see here is the efficiency of power conversion. The efficiency of power conversion has two reasons for being less than 1. One is because of the switch drop, the active switch drop Vt by Vg, and the other is because of the passive switch drop Vd by V naught. Okay. Now, we will take into account the non-ideality of the inductor also. We will assume during this analysis that the switches are ideal, but we will find out only the non-ideality of the inductor, and I have indicated in this picture RL, which is a resistance of the inductor winding. So, the method of finding out the voltage conversion ratio has not changed. It is still based on the volt second balance, but now we are accounting for the drop in the resistance of the inductor. Vg minus ILRL during the on period and Vg minus ILRL minus V naught during the off period, and if that is multiplied with the appropriate on time and off time and equated to 0, then we have now finally a relationship that the output voltage Vg is V naught into 1 minus d plus V naught into RL by R divided by 1 minus d. Now, this volt second balance gives a result where Vg is now related through V naught d as well as RL by R. Now, the additional functional element is the ratio of the parasitic resistance in inductor to the load resistance R, and if I define that quantity as alpha, then this relationship can be converted into the ideal result 1 by 1 minus d multiplied by a correction factor, which is 1 by 1 plus alpha into 1 minus d whole square. We see that the voltage conversion ratio when the inductor has a resistance present is the same as the original ideal ratio multiplied by a correction factor. This correction factor you can see is 1 by 1 plus alpha by 1 minus d whole square. This correction factor will be less than 1, because what you see is 1 by a quantity in the denominator. Denominator has 1 plus all positive quantities. So, this correction factor will always be less than 1. The efficiency also is the same as the correction factor. Whatever is the correction factor in voltage will turn out to be the correction factor of efficiency. This is because these non-idealities do not affect the current transfer ratio. On account of that, we find that the efficiency also is the same correction factor 1 by 1 plus alpha by 1 minus d whole square. It is much better to look at this function graphically, because it will give us a lot more insight into the operation of the converter and preferred operating conditions. We had earlier seen that the ideal power conversion factor, which is shown here 1 by 1 minus d, is a number which starts from 1 and goes to infinity as d goes to 1. But on account of this correction factor, when d becomes 1, the correction factor is itself 0. So, when you multiply both of them, the final result is 0, and this new function V naught by Vg now follows very close to the ideal function at lower values of d, but it diverges from the ideal function and eventually goes to 0, but it shows that we start from very close to 1. Instead of going to infinity, it reaches a number which is 0. So, naturally something which starts from 1 and goes up and eventually reaches 0 will have a maximum at some point. So, these are all of points of interest to us. What is this maximum that is reached? What is the value of that maximum? When is this reached at d? These are all something which we can find out. As I had shown, what is the duty ratio at which the maximum voltage gain is obtained, and what is that maximum gain, are the questions that can be found out by just analyzing this function. The ideal gain does not hold good anymore because of the correction factor. The correction factor has changed the nature of the gain, and the nature of the gain is such that we start from very close to 1, but we end up at 0 gain, and in between it reaches a peak and then falls down. So, let us try to find out what is the nature of this. This is very simple to do because this is a simple function in d and alpha, and if you want to find out at what value of d it reaches the maximum, this function has to be differentiated with respect to duty ratio and equated to 0, and that 0 occurs when alpha is equal to 1 minus d whole square. In this function, when the denominator terms are equal, that is when the maximum gain is reached, and that duty ratio is 1 minus root alpha. Alpha is the ratio of RL to R, and the maximum gain occurs when the duty ratio is 1 minus root alpha, and that maximum gain is 1 by 2 root alpha. This will be the maximum gain, and it will not be infinity, it will be something which is less than 4 or 5 or something, depending on what is 1 minus root alpha. For example, in the same converter, if alpha is equal to 0.1, if alpha is 0.1, then the duty ratio at which maximum gain occurs is 1 minus root of 0.1. So, that will be 1 minus probably root of 0.1, maybe about 0.3. So, that will be around 0.7. So, you will find that the maximum gain occurs at d equal to 0.7, and d equal to 0.7, if alpha is 0.1, we know that that maximum is 1 by 2 times root of alpha. Root of alpha is 0.3, 2 times 0.3 is 0.6, 1 by 0.6 will be about 1.7 or so. The gain is quite small if alpha is this number. Now, we can also try to plot the as we had drawn the corrected gain, we can also plot the efficiency of power conversion. Efficiency of power conversion is 1 by 1 plus alpha by 1 minus d whole square, and we find that when maximum gain is achieved at that particular duty ratio, the efficiency is only 0.5. This has a very serious consequence, because if efficiency is 0.5, then the converter has more losses than what is being delivered. The power that is delivered is more than the power that is lost, then it will not be a good power converter. So, we can even say that this region beyond this peak, where the duty ratio is such that the efficiency is less than 1 by 2, is not the preferred region of operation. What I had shown here is the yellow region here is before the peak of this gain, and that is the preferred region where the duty ratio is more than 0.5. And in fact, in many converters it will be better that it is somewhere close to 0.8 or so, so that the preferred operating region is not all the way to the peak, but something which is less than the peak. Okay. These are certain things which are different from the buck converter. There we had no maximum, but in this converter there is a maximum gain which is related to the non-ideality of the inductor. The output voltage ripple is the next non-ideality associated with that. In any converter, we like the output voltage to be steady and constant, but the switching performance, the switching nature of the converter makes it makes the output voltage to have a ripple, switching ripple, and naturally a performance measure which can quantify this is the ratio of switching ripple to the average output voltage. Now, that can be found out by how much of this current is being supplied to the capacitor and how much is coming to the load. The load part will be the average value of I naught. The AC part of the current will go into the capacitor, and that is the one which will produce this delta V naught. Because in any capacitor, if there is no current flowing through that, the voltage across that is constant. So, if there is a switching ripple, there will be a switching current in the capacitor. If the switching current is known, it is possible to find out the switching ripple. So, out of the inductor current, the DC part, the part of the current which is coming into I naught, we know that the current coming in I naught is this portion, and the average of that is the current going into the resistor. Average, this is going into the resistor, and from I naught of t which is coming from inside the converter, if you subtract this I naught which is going into the resistor, whatever is left with is the current that is going into the capacitor. So, as expected, this has two components. When the switch is on, the capacitor is discharging into the resistor because no current is coming from the load, and when the switch is off, the switch current which comes out supplies the load and also charges the capacitor. So, the hatched region is the current in the capacitor, and if you integrate that, that will give you the voltage across the capacitor. Integral of V C, the voltage across the capacitor is 1 by C integral I C dt. So, you will find that the capacitor current which is here, if you integrate that, so during the time capacitor is discharging, current will be dropping linearly, and during the time capacitor is charging, current will be following this curve, and then in one cycle during one half, during the on period, capacitor is discharging, and during the off period capacitor is charging, and we might take any one of this to find out this delta V naught. It is simpler to do it from the on time. So, during the on time, the current that is supplied by the capacitor is I naught, on time is dTs, and it is supplied to C. So, total charge I into T divided by C is the delta V naught, and I naught is V naught by R, the other quantities are dTs by C, and if you transfer V naught to the left hand side, we get the voltage ripple is now a measure which can be quantitatively expressed as duty ratio multiplied by Ts by Rc. Again, as seen before, the voltage ripple appears as a ratio of a period, time period of the switching and the natural period of the circuit. Natural period of the circuit is Rc, switching period is Ts, and if this ratio Ts by Rc is small, if this is very much less than 1, then we will find voltage ripple is also very small, and that criteria which is the design guideline for making sure that the boost converter has low output voltage ripple. Okay. So, what we have seen is that the ideal voltage gain of the converter. See, we have followed the same methods that we had done as before. In the boost buck converter also, we went through measuring several ideal quantities, several non-ideal quantities, then the non-idealities of the converter itself, the non-idealities of the inductors, the switches, and so on. So, the first quantity that we found out is the ideal voltage gain, and this was done by finding out the volt second balance on the inductor. From volt second balance, we found that V naught by Vg is 1 by 1 minus d, which is a good thing. We are able to convert power, deliver a voltage which is more than the input voltage, and that is the reason for this converter to be named as boost converter. As a next thing that we found was that the ratio of the currents, ratio of input current to the output current is also a function of D, and this also has the same ratio as the forward voltage converter. This is true in all the power converters where no loss is taking place. The forward voltage gain and the reverse current gain will be the same. And this follows either this follows the fact that in an ideal converter there are no losses, or because there are no losses you can say that one ratio is the inverse of the other ratio. Ig by I naught is same as V naught by Vg, or V naught by Vg and I naught by Ig are inverse of each other. The next thing that we found out, these were the positive things. Power is converted at a certain voltage and there is a ratio of current drawn from the output to the input. The third quantity is the non-ideal property. A standard linear converter will not have current ripple, will not have voltage ripple. It will draw current steadily and supply power steadily. There will be voltage gain, there will be current gain, but there will be no current ripple or voltage ripple. But in a switching converter, there will be current ripple and voltage ripple, because the process of power conversion involves switching, and the switching itself produces discontinuities in voltages and discontinuities in currents, and this reflects as a ripple current in all the storage elements, storage inductors, and a ripple voltage on all the storage capacitors. And we found that using the integral of the voltage across the inductor, it is possible to find out what is this delta IL and express it as a ratio of IL, and this ratio delta IL to IL is a normalized current ripple called ripple factor, and this ripple factor is a function of the duty ratio 1 minus d square and d, and it is also a function of the ratio of the two times in the converters, and these times are Ts and L by R. The switching period divided by the L by R time constant of the converter, and if we want this current ripple to be very small, we have to make Ts to be very much less compared to L by R. This also is something which we had seen in the previous converter, and we see that appearing again in this converter also. The next thing that we see is that the output voltage also has ripple. It is not a constant steady output voltage. Because of the power processing being discontinuous, we have delta V naught by V naught, which is a measure of the non-ideal voltage present at the output, and that also turns out to be a function of D and a ratio of 2 times. Switching period, if it is very much less than the output time constant, output RC time constant, then this voltage ripple will be quite small. So, we had seen that this converter boosts the voltage with the ratio of 1 by 1 minus d, and the current gain is also 1 by 1 minus d. The current has undesirable ripple, voltage has undesirable ripple, current in the inductor, the voltage across the capacitor. These undesirable ripple can be made as small as possible if we make the inductor time constant and the capacitor time constant with the load to be very small compared to the or the switching period very small compared to the L by R and R by C time constants of the converter. So, then we saw that the real voltage gain in the converter is not the same as ideal voltage gain. It has two non-idealities. One of them is the non-ideality because of the conduction drops in the switches, another is the non-ideality because of the resistance in the conducting paths. This can be in the source, inductor and so on, and both these non-idealities are modifying the voltage gain from the ideal value. This part is the ideal value, this part is the ideal value of voltage gain. This ideal value is now modified by a correction factor in both the cases. So, in the case of inductor resistance, it is modified by 1 by 1 plus alpha by 1 minus d square. In the case of switch drops, a similar modification, a correction factor exists, and it is possible to find out these factors applying the same principles of volt second balance on the inductor. The real current gain is not affected by any of the non-idealities, because all the non-idealities are associated as series non-idealities. Series non-idealities do not affect the current gain. You can see that the current gain for the real converter as well as the ideal converter are the same. The reason is whether it is a switch drop or diode drop, VD, VT or RL, RS, all of them are series non-idealities. They are present in as a series element in the circuit and they do not affect the current gain. They do not affect the current gain of the circuit. And the next measure is the efficiency of power conversion. The efficiency of power conversion again is consisting of two parts. When the inductor has a resistance or the conducting path has a resistance, that contributes to some losses, and those losses can be quantified and efficiency can be calculated as the ratio of 1 minus d whole square divided by 1 minus d whole square plus alpha, and the conduction drop of the switches are also contributing to losses, and on account of these losses again there is a loss in power, and that loss in power is quantified by the efficiency term that is here. So, as per this you will see that Vt by Vg is a critical quantity and Vd by this quantity Vg by 1 minus d is a critical quantity. Vt has to be very much less than Vg, diode drop has to be very much less than V naught. If that is true, then the efficiency will be better. Then the last point that we saw was the preferred operating range. We saw that the efficiency goes below 0.5 when duty ratio is more than 1 minus root of alpha. So, when you are in the range beyond this, the efficiency is less than 0.5, which is not a good operating condition. So, that the preferred operating range is limited to less than 1 minus root alpha, or in a real case it will be even limited much less than this quantity, maybe 1/2 of this. And this is because of the losses in the converter and efficiency dropping drastically as you reach the maximum gain. Okay. So, what we had seen up to now are the performance factors of the boost converter. This boost converter we had seen is a variant of the same switch cell, two switches, a single pole double throw switch, one number, and then an inductor. So, these two elements were combined together to get our boost converter. Now, the another way of connecting the same switch cell consisting of the throws T1, T2 and P is to connect the source on one of the poles and the load on the other pole, and then make the inductor and the pole of the switch to the third end, and such a converter is called the buck boost converter. And this converter has a similar set of performance features as we had seen before: the voltage conversion ratio, current conversion ratio, inductor current ripple, capacitor or the output voltage ripple, then the correction factors on the output voltage on account of non-idealities present. The non-idealities could be the switch non-ideality, the diode drop and the switch drop. All these factors of V naught by Vg, I naught by Ig, then delta V naught by V naught, then delta IL by IL efficiency. So, these are the steady state performance quantities. So, what we will see in the following lecture will be to follow again the same kind of methods, the volt second balance for finding out the voltage conversion ratio, current averaging for finding out the current conversion ratio, the balance, the integral of the inductor voltage to find out the inductor current ripple, integration of the capacitor current to find out the voltage ripple, then again modified volt second or fully accounted volt second balance on the inductor on account of the switching drops, on account of the resistances in the various parts of the circuit. So, all these contribute towards losses in the converter. To what extent these losses affect the voltage conversion ratio, to what extent these losses appear in the efficiency of the converter. So, in effect we will repeat the same exercise again in the next lecture for the buck boost converter, so that we fully understand the analytical method. The analytical method is very simple, only there are 5 steps. What are the 5 steps? The first step is the volt second balance on the inductor. This will give us what is the ratio of the output voltage to the input voltage. The second step is the averaging the current in the inductor. This will give us the ratio of the output current to the input current. The third step is integrating the voltage across the inductor. This will give us the ripple current in the inductor. The next or the fourth step is integrating the current through the capacitor, which will give us the voltage ripple on the capacitor. So, these are all the ideal and the non-ideal converter where there are no losses present, where every element is ideal. Because of the switching, you have the non-idealities of switching current ripple and switching voltage ripple. After these are accounted for, we analyze for the non-idealities of the switches. These are the conduction drop of active switches, conduction drop of passive switches, Vt for the transistor, Vd for the diode. They also affect the output voltage. They do not affect the current ratios because they are series non-idealities, and once we account for these things, we will get again the ratio of voltage V naught to Vg. We will see that I naught to Ig is not affected, and the same correction factor that we see on V naught by Vg will also be accounted as efficiency of the converter. So, to that extent there are losses in the converter. So, we will go through the same 6 steps in the next lecture with a few methods of or with a few examples, and once that is done, we are fully thorough with the steady state analysis of any converter. We might take a few examples after that and continue with more advanced converters, which will be isolated converters. Thank you very much.